Hi everyone. In this video, we're going to look at a hypothesis test involving comparing two independent means. So here's our sample scenario. Red Rock's teacher wants to know if students in the nursing program and students in the business program differ in their average weekly study hours. So they take a sample of 35 nursing students. Those students had a mean of 14.2 hours per week studying and a standard deviation of 4.8. The sample of 38 business students had a mean of 11.9 hours studying per week with a standard deviation of 5.3. And this is just made up data. This is not a real study that we did at Red Rocks, but just an example. I mentioned in the title that these are for comparing two independent means. We're talking about the mean from two different populations, the population of nursing students and the population of business students. And these are independent in the sense that the study times for the nursing students are not connected in any way to the study times of the business students. These aren't, the same students in different classes. If you want to compare means from, a group of students and their test scores in math versus English or something like that, those are not independent because they're sort of linked together, and that's a different type of hypothesis test. But if you have two separate groups or two separate non-connected sets of values, we can do this independent means testing. So step one in our process is to state the hypotheses. The hypothesis here, or the claim, is that the mean study time is different for nursing and business students. In this case, the claim is just that the two means are not equal. I'm writing this in symbols as mu sub n, indicating the population mean for nursing student study times, and then mu sub b for business students. So mu sub n is not equal to mu sub b. We're not claiming that one is higher than the other, just that they're not the same. The null hypothesis would be that they are in fact the same, and the alternative hypothesis is this claim that we're making that mu sub n does not equal mu sub b. I included an alternative way to state the null hypothesis here. So mu sub n equals mu sub b is also equivalent to mu sub n minus mu sub b equals 0. So you might see the hypotheses written in this form where you take the difference between the population means instead of having each one on either side of the equal sign. And because of the format here, this is going to be a two-tailed test. I'm not necessarily claiming that nursing students have a higher study time amount or a lower study time amount, but just that they're different. So this is two-tailed, this not equal statement in the alternative hypothesis gives us the direction. Step two in our process is to select the test statistic and the distribution we'll be using. When we're testing a claim about two independent means, we're going to use what's called Welch's t-test, and the test statistic formula looks like this. The test statistic is going to be the difference in the sample means, so x1 bar and x2 bar, x1 bar minus x2 bar. That's on the top. And then in the bottom we have a square root, and inside that square root we have S1 squared, that would be the first sample standard deviation squared, divided by N1, that's the sample size of the first sample, plus S2 squared over N2. So you have each of the sample standard deviations squared divided by the sample size. If we only had one of these in the denominator, this would look similar to the test statistic from the hypothesis test for single means, but we have both of them added together and then inside the square root here. This is going to be following a t-distribution, this sampling distribution, similar to our single mean case, but the degrees of freedom here is kind of a complicated combination of what the degrees of freedom would be for a single mean, which is generally just n minus 1. You can use a conservative estimate where you just look at n1 minus 1 and n2 minus 1 and take the smaller of the two. And you may see that on some problems, but in our class we're going to focus on the Welch Satterthwaite formula to compute the degrees of freedom. And you don't really need to worry too much about these formulas, assuming you're doing these calculations using technology, because the technology will just kind of build them in for you. I did want to point out here there is an alternate form of this test statistic that would be the x1 bar minus x2 bar minus mu1 minus mu2 on the top. Mu1 minus mu2, the difference between our population means, if we're assuming the null hypothesis for a two-tailed or for a two population test is always going to be that these two are equal. So this minus mu1 minus mu2 will always be 0. And that's why typically you see this formula stated without that piece in it. But if I include this piece, it kind of mirrors what we saw in the last section where we had x bar minus mu over s over root n. It has the same format, so I just wanted to point out that parallel. So after we've selected our test statistic and distribution, we need to identify our significance level. You can see more about this in prior videos, but generally we're just going to get this value from the problem. I'm going to assume we're using the standard alpha of 0.05 in this case. Then step 4, we need to collect our sample data. I've summarized it from the original problem here. And then we're going to calculate the p-value. So if you were doing this without technology or without Desmos, which is what we're going to use here, you would use this test statistic formula that we just looked at, plug in all the sample means and the sample standard deviations and the sample sizes, and then use the t-distribution and a t-table or something like that to calculate the p-value. But we are going to use Desmos for this. So I'm at desmos.com. I'm going to open the calculator or desmos.com/calculator, going to the same place as our last section. So the plus symbol that says add item in the top left corner. Fourth option is inference. I'm selecting that. And then we're going to use the same thing that we did for tests about a single mean, a t-test. And in this case, we have two samples. So whether I have the sample data and I put that in for sample 1 and sample 2, or in this case, I have the statistics on the sample. So my sample 1 had sample size 35. There were 35 nursing students. The mean was 14.2 hours, and the standard deviation was 4.8 hours. So that was our nursing group. And then the business students, there were 38 students. Their mean study time was 11.9 hours, and the standard deviation was 5.3 hours. So I'm putting this in for sample 1 and sample 2 in this case, and then I'm going to create the test. You'll see another t-test item show up in the list, and I'm going to open the hypothesis test section. The default null hypothesis is mu1 minus mu2 equals 0, which is equivalent to mu1 equals mu2. And that's what we want to use here. In our setup, we looked at mu sub n and mu sub b. I'm assuming nursing is the first group and business is the second group. So the convention is to label these either with letters or with numbers. So this is the null hypothesis I want. And because our alternative hypothesis was not a less than or a greater than, this is going to be a two-tailed test, which in Desmos is this both option. So you'll see that the test statistic shows up at the bottom. In this case, t is 1.946. That is from that calculation that I showed on screen earlier. You'll also see it shows the degrees of freedom, the 70.98. That is calculated using that Welch Satterthwaite formula in the background. And it's also given us the p-value, which in this context is the area to the right of this test statistic and this little right-hand tail doubled because we have this two-tailed test. So I'm imagining what's the likelihood of getting something this extreme either on the high end or on the low end. And this p-value is fairly small, but is actually just a little bit higher than our significance level. If our significance level is 0.05, then this just barely is above that. So when it comes to making a decision, we're saying, is our p-value small or small enough? In this case, our p-value is not quite small enough. It's pretty close, but not quite. And so we would fail to reject our null hypothesis here. The conclusion here would be that there is not enough evidence to support the claim that students in nursing study a different amount on average than students in business. Essentially saying that the differences that we see in these samples are not big enough to be confident that there is actually a difference. The fact that the p-value is very close to 0.05 means that we have kind of a borderline case here. This might be something where we want to investigate further with larger samples or something like that. We're close to having a difference, but it's just not quite significant enough. In this case, in the samples, I might have noticed that nursing students had a higher mean than business students. And I could have carried out a one-tailed test for this. So if instead of just claiming that the mean study time is different for nursing and business students, I claimed that the mean study time is higher among nursing students than business students, then our claim would be that mu sub n is greater than mu sub b. This does not change the null hypothesis, but this does now say that this would be a right-tailed test. If I go back to my calculations and choose a right-tailed test, now we're looking at the area just in this one right tail. And this p-value actually is less than the significance level. So our conclusion in this case would be that there is significant evidence to support the claim that students in nursing study more on average than students in business. And this feels a little counterintuitive that we don't support the claim that they're different, but we do support the claim that that one is higher than the other. And this is why you really need to formulate your hypotheses before you look at the sample. Otherwise, you can kind of pick and choose what you're claiming and what your significance level is and that kind of thing to reach a desired conclusion. So make sure that you are setting your significance level and your claims before you do the study, and then we can go with the conclusion based on the p-value. And also recognize that the smaller the p-value is, the stronger the evidence we have for our alternative hypothesis. So hypothesis testing isn't quite as black and white as we make it out with the reject and fail to reject conditions, but we're using that p-value as a measure of how unusual is this test statistic or is this sample compared to the null hypothesis. Based on our original question, our conclusion would be still to fail to reject the null hypothesis and say that there's not enough evidence to support the claim, the original claim, that the students in the two programs study a different amount. That's it for this video. Thanks for watching.